Hello everyone, welcome to Natural Language Processing. And in this session, we are going to discuss about a project which is going to be how to generate poems with the help of our natural language processing. And in this process, we are going to create poetic text generation using LSTM. And especially here, we go into a new LSTM, which is we are adding few more functionality to it. So, what is that functionality and how we are going to achieve it? Let us see in this particular project. Looking into the introduction, poetry, a timeless art form, has found new life in the digital era through the help of literature and technology. And using natural language processing techniques, we are exploring how computers can create poetry on their own. And long short-term memory network offer a solution, allowing machines to understand and produce poetic language more effectively. And with the help of this particular architecture, we are going to bring back the context or the style of William Shakespeare, one of the famous poet. And here we are going to take some of the sonnets, which is a piece of poem from William Shakespeare. We take it, we give it to our model to train so that it gives us a result. The next word prediction. So you predict a word and then you give that word as an input to the next input and then you predict the next word. So in that sequence, we will create a poem or a paragraph like that. So that is our task. Like that, if you have some more, if you are interested in some other poetic literatures from some other creators or poets, you could take their data set or you could mix to get a combined version as well. And looking about the data set, once again, this is from the same site as we have used in the previous session. So the Shakespearean Sonnet by William Shakespeare are a timeless collection of poems that serve as an invaluable data set for various natural language processing tasks, particularly poem generation using LSTM. Crafted by the brilliant poet Shakespeare, these sonnets offer a rich array of linguistic structures and emotional depth, making them an ideal resource for training language models and exploring the nuances of poetic expression. Yeah, so I told you, right, we are going to utilize a different architecture here, a modification to LSTM. So the problem with LSTM and what is the need of here implementation, we will be implementing bidirectional RNN or LSTM. What is the need of it and how to achieve it? Let us see in this particular session. Starting with bidirectional, I'll tell you what is the need for this first. We already have a LSTM which works well to some extent. For our previous tasks, it worked really well. So the traditional neural networks and long short-term memory networks are powerful tool for sequential data processing, capable of capturing dependencies in one direction, past to future. However, they miss important context information that lies outside their directional scope, which is something like, for example, they go from the past to the future words. Something like if it starts, we have two sentences. So your LSTM starts by looking into Raj. Next, it takes apple, likes, and then takes apple. So when it reaches apple, it gets the previous words as well. Raj likes. Then it goes to he, it gets all the three words from the previous. Here also we get the same. So like this, it goes from past to future. And here Raj likes apple has a meaning. Here also Raj likes apple, but if you look at the context of the remaining things you have in the future, he eats it every day. So here the apple refers to the fruit apple, but here Raj likes apple. Their phones are expensive. It refers to the technology or the company Apple, which produces mobile phone. So the context may be dependent on the future upcoming words or even sentences you have in your particular paragraph or your corpus. So it is required to understand your future words, entire words, and then come back and have the meaning or interpretation here. So that will be a best way, but our traditional RNN works in such a way that it looks from past to the future. What happens next is a question mark, you don't get it here anywhere. Okay, so that's how they pass the information. So here it will get the past. This won't know that what it is going to receive in the future or in the upcoming timestamp. And to overcome this, they have introduced something known as a bidirectional layer, which is just an additional property to it, which gives us a lot of advantage here, especially bidirectional RNN or LSTMs address this limitation by processing the input sequence in both forward and backward direction simultaneously. So now instead of past to future, you get from future to past as well. So it goes in both direction, both the forward and backward, and this enables the model to capture information from both past and future contexts, providing a more comprehensive understanding of the input sequence as well. So this is what especially happens in a bidirectional. Now, for example, you pass your input to LSTM. Usually, let us ignore all these complex steps. First, we are focusing on this input and this green color signal and the output. We know our LSTM produces this, right? It's RNN, but anyway, if inside process changes, it's LSTM. The timestamp input passes, previous feedback, process happened, output generated, feedback goes on. Similarly, here you pass the input, LSTM produces the output, at the same time pass the feedback, gets the next word, process and produce the output, gets the feedback, similarly together it process and then gives another feedback. So maybe this is the last word you had. After this, what happens is it is not entirely passed outside. All these outputs are waiting here because there are few more steps to follow. Once it reaches the last word, now it is going to start and pick from the reverse way. So this feedback is now provided from the last now. So it kickstarts. After this last word is provided to LSTM, which produces a feedback. So in reverse order you are processing. So the next will be passed. So this word is given to this LSTM. It produces output, at the same time it produces feedback. It's the LSTM. It receives parallelly in the reverse order as well. And what happens is this output is concatenated or added here with the reverse output as well, which is something like you are processing now the words forward and backward. And what is the context of the word time in the forward plus the context of the word time in the backward, which has this meaning as well. So in both the direction, and it is helpful in both the ways where you are looking into the future and getting this context as well. And this is why we call it as a bidirectional. Simple. For this word, what is the forward way and what is the reverse context, you both concatenate and pass to the next set of layer. So in this manner, if you process it is bidirectional LSTM. And in this particular manner, we are going to implement in our project as well. And this project, we will be running this to many epochs, something like 300 and all. So I have ran it already and I have it. So we'll be explaining and going through and make an inference with it. And for this particular process, we know that Google Colab cuts off every time. Even though you would have seen some of the times where for me also it cut it off. And when you run it for long epochs, it is not suggested to go with Colab because we have a temporary storage there. It can cut off anytime and it will be really frustrating. For these kind of long-term problems or long-term process, we could prefer something known as Kaggle Notebook. So in Kaggle, you can go, Kaggle we have downloaded datasets. You could click this plus and create a new notebook. You will be getting this notebook and you have the GPU versions and all you could select the name. It's similar to Colab, okay? And you have this particular option where you can decide what is the datasets. I have uploaded the sonnet dataset of William Shakespeare, sonnets txt file. It is available here. This is the txt poems which we have. As well as you have this, you could copy the path from here. The output will be stored here. You have the accelerator. I am using GPU for faster acceleration. We have our programming language. All these things can be stored here, and you could, if you save this version, you could save. Quick save means it will just save it, or if you save and run all, what all things you have done, it is going to kickstart automatically and run it from the start to end. Maybe if you are running for 12 hours, it can run for maximum of 12 hours. So if I want to run many epochs, I could just save it, so and run and commit will run freshly. And if I store the models finally, it could just generate the output so that I can pick the model file which has ran for many hours without any disturbance. I can save it. Or if you have any minor errors, it is going to just cut off at that place and it will end. So I have to be careful in that way as well. So we kickstart now with the dataset sonnets.txt. Let us do the process here and see. So we are importing NumPy, Matplotlib, TensorFlow as TF, OS, and we have sonnets.txt in our Kaggle input. So I am picking, I am taking the text and I am reading it. I am getting a word length of 93578. Okay, so this is the total count. And if you look at, for example, the Shakespeare text dot lower and split all the new line character. So whenever you had new line, you are changing them into now sentence tokens. So you have all the poem lines here. Now, as we know that we used to create tokenizer and tokenize it, right? So we go with tensorflow.keras.preprocessing.text. We are going to create the tokenizer. And we will be using something known as padding as well here, which we haven't used in our previous session. Let me explain. When we reach there, I'll tell you why we haven't used padding there and why we are using padding here. And here we will be going with bidirectional as well. Let us discuss all those concepts here. So we have the tokenizer. First, we used to fit on text, and you pass your entire corpus here. You will be getting the vocabulary size plus 1. So you get all your word index, which is the total word count, plus 1 will give you the vocabulary size. You have 3211 words here. And then I want to create n-gram sequences. See here, the input sequence is a list, and for line in corpus, so for every line, I am picking the tokens and I am tokenizing into sequence. And then what I am doing is 1 comma the length of token. Maybe for example, if I have a sentence maybe of something like which has maybe you have, he is not a coward, he is ready to be a king. Maybe you have this. So what this is going to do is 1 comma the length of it, which means it starts from 1, which means he. So you are starting from 0 and ending plus 1. So it starts from he 2, right? So it starts from 1. So I will be 1 plus 1 will be 2. So it's 0 is to 2 will be having 1. So he is. Then the next time it runs, the value of I increases. So it will go and create he is not. Then the next is he is not a. Then it will be he is not a coward. Till it will run like that, it is going to create n-gram sequences till it reaches the end. And if you look at the input sequences, and maybe I'll just show the first 10. Okay, so this is what happens. So this is a context of 1, 2, 3, 4, 5, 6 words. So it is creating from 2, bigram, trigram, 4 gram, 5 gram and 6 gram. So based on each word, it is going to change. Maybe something like, let us pick the last one. Okay, and let us try to slice it to, okay, it should be in the reverse way. So you could see, right? So each sentence may have different word count here. This is a problem actually, because our neural networks actually, when you train your LSTM or anyone, the input length should be of same size. Okay, if you go with the tabular data, it's not a problem. It's not a big deal, because they always, you will pass 10 features means you will pass 10 features. But in our previous session where we had utilized the next word prediction, our data set is actually something like you pass one word as input. Okay, so you pass some token as input, you get a respective token as output. Maybe if this is the word, this is the next word. This is what we have mapped, and all our input, maybe something like if 13 is the input, you get another word. Maybe something like if he is the input, then is could be the output. If found as the input, then her could be the output. So like that, we had a constant size in feature, but here it is not. Here you may have grams, so it could be 3 sentences, it could be 5, it could be 7, and the range changes. You can't fix a definite size as well here. That is a problem, and to handle this only, we will be going with something known as padding the sequence. So what is padding is, maybe something like here we did something, right? Maybe I'll get it back. I hope we have defined some examples somewhere here. Okay, not here. Yeah, here it is. Okay, I did this right. Maybe I'll just pick it. And maybe something like what is padding is you set a common size. Maybe we'll have this as a common size, means totally all for these sentences. Maybe we'll keep this as a common size, which is 5 words. So here it is 4, right? So you are just going to add a 0. Okay. Here you will be adding 2 zeros, so that totally the total count matches. Here we will be adding 3 zeros, so that the total count matches, and it will do the process for us. Now everything is of size 5, and he is going to be in number representation like this. So everything is of similar size, and that is called as padding. To make them of similar size, we will be adding zeros, and these zeros you could add in the pre, which means in the beginning you are going to add. This is post padding, where after the words end you will add a padding. You have a maximum length as well, and you have a pre padding which adds in the before or after, so that is padding. And what is the maximum length is my maximum sequence length. Okay, so the maximum sequence length is 11. So I have a sentence where maximum length is actually 11. I have found it, and what we'll be doing is we'll be picking that. Okay, so for I in length, who is the maximum, I'm picking it. So if I run this, I'll be getting a list of all the length of my input sequence, and I'm picking the max from it. So that's the maximum of 11 is there. So take or make everything as 11 by adding zeros in the beginning. So that is free. And this we are doing with the help of TensorFlow, Keras, pre-processing sequence, where you have pad underscore sequence. You should pass your input, maximum length you want, and padding pre or post. So this will make sure your output is padded. And after that, if you look at this input of sequence of array, maybe we look at the first 20. So this is the padding of pre which has been done. So you can see zeros has been added to match the total length, and this is the reason for padding. And the maximum where we had 11 will have all the features, otherwise we will be having zeros to match the size. If now it is ready for us for the next task, and what we are going to do is we are going to split them into x and y for the next step of processes. And for that we need to split it, and if you just slice it, for example, you are slicing it all the rows, comma, colon of -1, okay, will give you something like maybe we'll use Control Z and see this 20 as such, and see this to see the result or change. You can see I'm getting all these things without the last column, which is 34. Okay, so the next 417, 877, I'm getting till this, and I'm just leaving this as empty, or I'm not considering it for my x. So this is what I have stored in x, and my y is nothing but, okay, I'm just taking the last one. Okay, so I'm just taking my last one. Sorry, it should be -1. It's not till, it is just -1. Will give you the last column here, because what I'm telling here is if this is the sequence, this is the next word. If this is the sequence, this is the next word. If this is the sequence, this is the next word. So for that, this is my feature, still this is my feature, this is my target, and that's what exactly we are doing here, as taking till -1 till the last. Just leave the last and take just the last, and this will make sure you take all the rows. And once you've done this labels, I'm turning it as usual like our previous. We have to turn them into categoricals, where we use TensorFlow, Keras, utils to do it. The number of vocabulary size you have, it will transform, and you have our x in this shape, and you have x should be of 3 dimension when we go with bidirectional LSTM. So we just add extra layer to it. For example, if you look at x, you have this, right? And if you look at the small x, where I have done this expand dimension, it is going to add one extra of 2D. One single dimension gets added overall, so you get something like this. That is your expand dimension, which we have done in small x. And we have this additional dimension now, and the vocabulary size is 3211, and your y is now features are ready, right? So features has been turned into categoricals. You get it as this format. Everything is ready. Now it's time for us to create our neural network. So from TensorFlow, Keras, pre-processing, sequence, we pad sequence. I hope we already used it. So from layers, we are using embedding layer, LSTM, dense. We'll be using dropout. I'll tell you what's the use of it. And we are going with the bidirectional. So this bidirectional is going to help us for that particular process, bidirectional LSTM. And then tokenizers, sequential. Optimizer, earlier we have gone with Adam by just mentioning as a string in the compile. But there you can't optimize the learning rate. Remember, the learning rate is the lambda value which determines how slow or fast you are updating your weights and params. Here you can use, if you call from the TensorFlow itself, you can pass the learning rate as a parameter. If you want, you could adjust it to a smaller value or some larger value. Anyway, they will be around 3-4 or 1e-4 or something like that, 1e-2 or 0.01. All these things you could alter with it. Then if you want, you can add regularizers, then we'll be utilizing other stuffs as well. So going with model creation sequential, I'll add an embedding layer of vocabulary size 100, and the input length is equal to maximum sequence length -1. 10 could be the maximum. So that's what we define here. And I need to just represent them in a vector size of 100. Then how to add a bidirectional LSTM is you have your bidirectional layer, right? For the input of it, pass your LSTM. That is your bidirectional. It is going to do both the process and gives you the next output. And this is 150 and then return sequences is true. Then I am adding a layer called as dropout. Dropout is actually something like we want to avoid overfitting. Overfitting is something like your model or a network trains too much on the training data, so that when you give new data, it won't perform well. It will just stick to the training data. For that, what I'm telling is dropout of 0.2 means when you pass through this layer, whatever things has been learned, it is going to forget 20% of the data. It is going to just remove it. 0.2 is 20% here. So we just forget every time so that it loses some information, not just stick with that. To avoid overfitting, we go with dropout. Then I add a LSTM layer. Then I add a dense layer of 1024 activation ReLU. And the kernel regularizer is L2 regularization. So this is to once again avoid any overfitting. So you can add regularizers here. You have L1 and L2. These are different methods to avoid overfitting. Then we have a dense layer with vocabulary size my output. The output layer, right? Softmax with how many words you have, I need to get till that. And when I compile, I need to go with categorical cross entropy, optimizer as Adam, and metrics here as accuracy. And yeah, so you could optimize this as well. For example, okay, so maybe we could do this, or we could experiment with this model as well. So both of these are available. So you could go, if you want a simple steps, you can go with this. Or if you want complex, you can train with this as well. Or if you are adding Adam, so you have to compile with optimizer Adam, and this is the learning rate which we have optimized. So you have to set whatever you prefer, you could run. And we are going to run with the latest thing, which is this, a simple one. We just get the input bidirectional and produces the output. So we finally compile once again with the optimizer Adam and the metrics as accuracy. And I'm not setting any batch size here, so it is going to finish it on its own. And history and the model is fitting with X and Y. Epoch is 300. So I have ran it for 300. You can see the loss has been from here, and accuracy is just 0.0224. And after it reaches 300 epochs, after some time, it has ended with an accuracy of 0.77. Till it could be greater than this. So we need to adjust with some complex architecture to proceed in this manner and get some nice output. And the loss function here, loss has reduced to 0.88. It's a good sign. It has reduced under 1, closer to 0. So now our model is ready. So if you want to make inference, actually this once again, if you pass a sequence, it produces the next word. But if you want to create, it will just give you one word. But if you want to create a poem that is of multiple words, then we need to create a loop. Maybe if you want a poem of size 100, so I'm just running this loop for 100 times. Every time I'm starting with a seed text of it's a cold night, it was a cold night. So this turned into sequences. Then padding has been done for 11 max. And then it is going with a prediction argmax. Okay, it passes the input and get the output. So you get the output of which word is the predicted one. So the output word will be there. So the predicted, what we will be doing is we pick what it is, where it is. Okay, we'll just turn it back. Okay, if the word is inside the predicted, we pick that word and we will be adding. So what is my output word? I'm going to pick that. Okay, after finding the word, turn them into word, and then I'm just adding it with my seed text. Maybe it was a cold night and the next word is then. So now it was a cold night, then will be the next seed to kickstart here to turn that combined thing into token. Then the process happens to predict the next word, then that sentence once again. So it adds sentence by sentence, word by word, it is going to once again process to predict next word. So how many words you have asked, that many it is going to run. So for example, I'll start with this, it was a cold night. So it is making prediction every time. And finally, I'm just printing the seed text, which is my output finally. So it was a cold night by lies in thine own dear shy. Thy love both be behold. So the Shakespeare sonnet will be something like this. It has made predictions till the 100 word. So for next I'm making something like the next 200 word predict from here. So this is from the sonnet itself. So it is making the prediction of the 200 next 200, and it will give you the respective result, which is going to be something like yeah, it will run. So being your slave, what should I do? But tend to me when cannot themselves attain. So it goes. So the poem has been created. And here, compared with the previous project, simply we have just had a sequence as an input, multiple words. So we had done padding. So whenever you pass a sequence, you have to make sure they are of same size. So you have to use padding to it. And then if you are passing bidirectional, we have seen what is the backend or math behind it. You just do concatenation for each layer, and the feedback from both the sides has been passed, and finally they'll do this process. And one more thing is here we are adding dropout for forgetting as well, but we have implemented this simple version, and you could also do this complex version to see how it is improving from this as well. And bidirectional LSTM, that's a simple process compared with our previous session. This was a simple upgrade and implemented. We used a loop to do that particular next word prediction based on the context. Actually here we had a max sequence of 11, right? So it is going to do that particular process. And yeah, so if you have maybe like if you go for 100 words, because here we could do something like because if you going for 100 words, after 11 words the next time it will be 12, but here we are doing a pad sequence of max length maybe 10, then it actually cuts off. So for that we could even modify something like if the word length is higher than that, you could just pick the last 10 words so that the size matches, don't go beyond the limit. Anyway, it will cut off on its own, and you could do it manually as well. And we had made prediction and got our respective result here. So that's it for this session, and we'll see you in the upcoming session. Thank you.